Good evening, friends. Study with the Pal Engineering and General Geology Parvin Singh book. So in chapter 11 में हम silicate group पे हैं chemical compositions. तो most common silicate minerals are made up chiefly of a few of the following 9 elements: sodium, potassium, aluminum, calcium, magnesium, iron, lithium, silicon, and oxygen. Other elements are present only rarely and in trace, notwithstanding the fewer element that go to make the silicate. The varieties and complexity of a chemical composition of a silicate still remain most challenging assignment for a chemical mineralogist. In some cases, it may be impracticable to express the chemical composition of a silicate by simple formula, atomic structure. As a result of studies using latest techniques like X-rays, a vast amount of information has been collected about the general constitutions of silicate. It will be beyond the scope of this book to discuss the atomic structure of the silicate. Only the most important conclusions are mentioned below. The fundamental until all silicates are simple or complex repetitions of a fundamental silicon-oxygen tetrahedrons represented by the formula SiO4. In this tetrahedrons, the very small silica ion is situated in the center and is surrounded on the four sides by relatively big 5 times in size oxygen ions. The dimensions of this unit cells of silicon oxygen tetrahedrons are constant. Further, the distance between the silicon ions at the center and the oxygen atoms at the corner is 106 angstroms. So in this figure, this fundamental unit is repeated linked and joined in different ways, giving rise to different types of silicate structure. Independent tetrahedra. A unit SiO4 tetrahedrons has 4 negative charge, hence it has the capacity to exist as an isolated or independent tetrahedrons, provided these 4 negative charges are balanced by 4 positive ions of other metals. This actually happens in nature in orthosilicate. Thus zircon and magnesiums, which have 4 or 2 valences, respectively, easily combines with an independent silicate ions, giving rise to a zirconium silicate SZR SiO4. Sometimes more than 1, 2, 3 or 4 elements may combine with an independent tetrahedrons to satisfy the 4 negative valence, giving rise to different types of minerals. Oxygen, this important diagram. Double-linked tetrahedrons, in some cases SiO4 silicate group, may first get linked together in such a way that one oxygen atom is held common between the two cells. The net negative charge left in the two joint tetrahedrals is S6 oxygen-silicon molecules. And the formulas for such a coupled tetrahedron is Si2O6 minus 6. In fact, it is known as a Si2O7 group, this silicate group. This doubled tetrahedrons is also capable of independent existence when its 6 negative charges are satisfied by equal number of positive metallic element. Complex linked tetrahedron. In some cases, 3, 4 or 6 tetrahedrals may be linked together in such a way that they forms a closed ring type structure. The chain structure results from single dimensions continuations in which each tetrahedron is linked to an adjacent tetrahedron, one on the right and one on the left, by sharing the two corners. In other words, each silicon ion holds 3 oxygen ions in accordance with the General's formulas RSiO3. This is the characteristic structure of pyroxene group of a silicate and is commonly referred as single chain structure. So this important diagram. A double chain Dimensional continuations is also possible according to formula Si4O11 6 minus charges. The amphiboles group of minerals have been found to exhibit these types of double chain extensions. So double chain structure, these will have 6, 8 and 12 free negative charge to be satisfied. Their formulae are expressed respectively as Si3O9 minus 6 charge, Si4O12 minus 8 charge, and Si6O18 minus 12 charge. A large number of complex silicate have more than two fundamental tetrahedral linked together in the above manners. Repetitions in space. The single tetrahedrons and the double linked tetrahedrons as described above may in themselves be repeated in space in a variety of ways, giving rise to different structural forms in the silicate mineral. Among these structural forms, the following are of common occurrence. The sheet structure. The two-dimensional continuations of silicon tetrahedrons commonly result in a layered or sheet structure. It is characterized by the linkings of the tetrahedrons in such a way that all the three axes of one tetrahedrons are linked with an adjoining tetrahedrons, resulting ultimately into a hexagonal patterns repeated lengthwise and breadth-wise. Such sheets may be linked with others identical sheets resting above or below through metallic ions, resulting in a considerably weaker bond. This is the most characteristic atomic structure. The sheet structure of flake is platy and lamellar minerals like micas and chloride. Thank you.